All right, up until this point, you guys have been finding the derivatives of polynomials using the power rule and the constant multiple rule, products of two things using the product rule, derivatives of rational functions using the quotient rule, and derivatives of the trig functions. If you look back at every single function that you've taken the derivative of, though, you've never had an instance where the polynomial was raised to a power, or the angle that you were taking the derivative, or the angle that you were taking the trig function of, was always just x. It was never more than that. So if you take a look at the following examples of the polynomials, or of the different functions shown here, we've got a polynomial that's being raised to a power. That's something we've never done a derivative of. Up until this point, maybe it was raised to the second power, and you would write it out as two of them and then do product rule. But it's never been more than a second power. Additionally, we've never done a trig function that's been raised to a power. And we've also never had something like this where it was a trig function and then the angle was more than just an x. In order to do that, we would have to use something called the chain rule. Before we show the notation, which is on the next page, which is kind of scary looking to be honest, we're going to look at an example of how this comes about. And if you remember from last year, you were dealing with something called composite functions. That's where one function is based off of another function, essentially. So we're going to start it off and break it down into this function here, y equals 10x plus 12. What I'm going to do is I'm going to factor out a 2, and if I do that, I end up with 2 times the quantity of 5x plus 6. And this right here is a composite function, and it's basically saying that we rewrote it, saying that y equals 2 times u, where u took the place of this entire thing. Okay, so it's a composite function because it's y is a function of u, which is a function of x. Okay, so u is a function of x here. So this is where, I'm always harping on you guys to be really constant and cautious about your notation that you use. So this is why, because now we're going to have more than just y's and x's. We're going to have different things involved, and I talk too much, so I'm moving on. How do the derivatives of all these functions relate? Well, let's start off with the derivative. If you have y equals 10x plus 12, let's just start off with the original function before we did the composite notation. If you take the derivative of that, you get dy dx equals 10. Now, when you do the composition, y equals 2u, where u was 5x plus 6, and now you take the derivative of each of those pieces respectively. Dy du, the derivative of y with respect to u, is just 2. And the derivative of u with respect to x is just 5. Now if you look at the derivatives here, dy dx is 10, dy du is 2, du dx is 5. Take a look. If you multiply these two guys together, you'll get the value of the original derivative. Okay, so that's the chain rule shown in a composite form. Let's go ahead and take a look at example 2. By the way, you're probably looking at example 1 saying, why would I go through all that extra work? We're just laying the foundation for where the chain rule comes from. So for example 2, I'm going to actually get a thinner pen here because I'm going to write a little bit more on this one. Create a composition function for y and find the derivatives of y and its composition functions. Let's start off here with y equals 3x to the 4th minus 12x squared plus 1. If you look at this, the only way to make a composition of this guy is to factor it. So the first thing I'm going to do though is I'm going to do the derivative of the original function before I worry about the compositions. And if you do that and you bring down the 36 is just a constant multiple. The derivative of x to the 4th is 4x cubed. The 12 is a constant multiple, then the derivative of x squared would be times 2x. And the 1 is a constant, which is being added, so that just goes away. So the derivative of y is going to be 144x cubed minus 24x. Okay. So now let's look on making this a composition. and showing you how the composition will get you the same derivative if it's done properly. We're going to factor. This actually ends up being a perfect square binomial multiplication. So this is going to be 6x squared and 6x squared. It's going to be 1 and 1, and we're going to do subtraction. You can rewrite this now as 6x squared minus 1 quantity squared. So here's our composition that we're looking at. You can rewrite this as y equals u squared, where u is a function of x, and it's 6x squared minus 1. So again, all I'm doing is I'm rewriting this as a composite function. If you take the derivative of y with respect to u, you're going to get 2u. If you take the derivative of u with respect to x, you're going to get 12x. And I'm actually going to go a step further, and I know what u stands for. U is really 6x squared minus 1, which would make this 12x squared minus 2. If you take this derivative and you multiply it, just like we did in the previous example, you multiply the dy du times du dx, FOIL it or distribute it out, and you'll see that you get 144x cubed minus 24x, just like we did over here. Okay, so if I gave you this problem originally, okay, and I didn't give it to you in the polynomial format as it's shown up here, okay, so if I gave it to you in this factored format, we can rewrite it as a composition and then just multiply the two derivatives together, and as you can see, you end up with the same derivative. Okay, so make a prediction on what the chain rule says. Go for it, pause, and then go on to the next page. Okay, the notation on this is actually quite frightful if you just look at it at a glance, but let's talk through it slowly and see if we can make this make sense. F is going to be differentiable at the point u, where u is a function g of x. As long as g is differentiable at x, then the composite function will also be differentiable. So if you remember from pre-calculus, f of g of x can also be rewritten like this, f of g of x. The derivative, f of g prime of x, is just going to be the derivative of f of g of x times the derivative of g of x. Okay, again, this looks way more complicated than it really is. The notation that we used on the previous page kind of looks something like this. If y is a function of u and u is a function of x, then the derivative dy dx is going to be each derivative respectively multiplied together. Okay, so again, you've got two different mathematicians fighting on the proper notation for this thing. I'm going to talk you through the worked example. And just like you guys saw when we did instantaneous rate of change and then I showed you all these shortcuts, get it? Shortcut. So the same thing here. I'm going to show you the long worked out version of it using the full chain rule, and then we're going to show you the shortcut and the techniques to go about finding these derivatives a little more easily. So the first thing is find the derivative of f of x equals the cosine squared of the quantity 3x squared minus 1. So here we've got a lot going on. It's not just a trig function anymore. It's not just a polynomial anymore. We've got a whole bunch of composite functions going on here. So the first thing that you are always going to do, always, is take this power out of in the inside of this trig function, because this can be rewritten just like this. The cosine of 3x squared minus 1, that whole thing is squared. That's technically what the squared right here means, outside of the cosine. Okay, so I'm going to break this down like I did on the previous page with composite functions. The first thing, I've got something being squared. So I'm going to replace that with a g, and I'm going to show that g is going to stand for the cosine of 3x squared minus 1. Then I'm actually going to break down this function even more. I've got the cosine of this blob here, this mess. So I'm going to say, let's let g equal the cosine of h, where h is going to take the place of all that stuff. Okay, so now we're going to take the derivative of each function respectively. So if I look up here, f equals g squared, well, you can take the derivative of f with respect to g, and that would just be 2g. Then you can take the derivative of g with respect to h. So dg dh. Derivative of the cosine of h is the opposite sine of h. And then we're going to take the derivative of h with respect to x. And you're going to get 6x. And by the chain rule, if we multiply each respective derivative together, we will get the derivative of the original composite function. So df dx, because that's originally what we were given. We were given f as a function of x. So df dx, and I sound like I'm speaking different language right now, is going to be df dg times dg dh times dh dx. Sounds like fun, right? So df dg we found to be 2g. dg dh was negative sine of h, and dh dx was just 6x. Now, in order for this to be proper, this is supposed to all be in terms of x. So let's continue to substitute things in. H we know, h is 3x squared minus 1. And then g we know is the cosine of h, where h is 3x squared minus 1. So cosine of 3x squared minus 1, that's what g was. So that gets substituted in. Now everything is in terms of x. Okay, so you're looking at this and your eyes are spinning. You're like, I don't want to have to do 3 different compositions to make up one function. That's a lot of work and I don't want to do it. So, all right, well, enter Shrek. Everybody loves this movie, right? And if you don't, you've never seen it, go watch it, people. Okay? Because it can be cumbersome to create all these composite functions and take derivatives of each function, you can attack this using what I call the Shrek method. Ogres are like onions, and they have layers. So you're going to peel the layers of these composite functions from the outside to the inside. So now, just like I showed you all the shortcuts for the derivative, and you were like, oh, that would have been nice to know originally, well, we're going to jump right to the shortcut for the chain rule. So find the derivative of f of x. This is the same function that we had previously in this worked out example. So the first thing that I'm going to do is the same thing we did up there, and that was to pull the square away from the cosine and pull it to the outside. Okay, now notice I didn't do any derivatives. That's why the notation is f of x and not f prime. And now what you're going to do is think of this as layered, a layered onion. And your outer layer, the outermost thing that's being done, is a square. You've got something being raised to the second power. Well, apply the power rule then. F prime of x. Okay, so if you have something being squared, you would bring down the 2, and then you would subtract 1 from the power. Well, what was being raised to that 2? Cosine of 3x squared minus 1 was being raised to the second power. So that's what goes back inside. Okay, so that's the outer layer derivative. Now, go back to the original function. That piece is done now. So now what's your next layer? The next layer is the cosine. Cosine is being taken of something. So the derivative of cosine, and we're going to multiply all these pieces together, by the way. So the second layer is cosine. The derivative of cosine of something is the opposite sine of that thing. Well, what were we taking the cosine of originally? We were taking the cosine of 3x squared minus 1. So the derivative of that would be the opposite sine of 3x squared minus 1. Go back to the original. We're now done with this layer. And we've got one more thing left, and that is the 3x squared minus 1. So if we take the derivative of that last piece, we're going to have a 6x. And we are done with that piece. All right, so if you take a look at this, we've got outer layer, middle layer, inner layer. And if you take a look at what we came up with up here, we had 2 cosine of 3x squared minus 1 times the opposite sign of 3x squared minus 1 times 6x, and that's exactly what we got here. Okay? You have on the next page a couple of practice problems at the top only. I want you to do those problems by class time. And if you have any questions, make sure you ask me before we get started. Have a lovely evening all. Bye-bye.